Today we are going to focus on one of the next important topics, that is ergodic random processes. Basically, we are having two types of averages with respect to the random process. First one, we are having time averages, that is averages of the sample data over the time, and the ensemble averages which we have learned previously here. The definition of ergodic random process is as below. A random process is said to be ergodic if the time averages are equal to the ensemble averages. So any random process possessing this characteristic where time averages will be equal to the ensemble averages can be classified under the ergodic random process. First one, just look into one of the questionnaire. Show that for ergodic process the mean of the time average is equal to the ensemble mean. The solution for the above problem is as follows. Let x of t denote the averages of the sample data over the time. We can see the angular brackets here, then the random process x of t is there, and angular bracket means the averages of the sample data which are taken over the time here. Now this quantum averages of the sample that is data, this statistical average value is equal to the limit as t tends to time period tends to infinity, where 1 by t is and integration is multiplied with the integral of minus t by 2 to plus t by 2, then the random process and its samples x of t dt. You can take x of t is equal to, apply the limits here, then 1 by 2 t is there, integration minus t to plus t. So therefore from minus t to plus t we are having totally time duration is 2 periods of the time periods t are available. So therefore this becomes 1 by 2t, then minus t to plus t x of t into dt. Now the mean of the above that is average of the sample data. See, the above equation denotes the averages of the sample data as denoted here. The mean of this quantum in continuation with the above equation here, the mean of the x of t or averages of the sample data is given by expectation operator. Apply the expectation operator on the above equation here, that is averages of the sample data. If you apply the expectation operator, we get the mean of that particular quantum. Therefore E of that is expectation of averages of sample data, that is x of t, is equal to E of whatever is there on the right hand side, that is 1 by 2t integration between minus t to plus t x of t into dt. This becomes equal to 1 by 2t integration minus t to plus t, then expectation operator is applied inside over x of t, then dt here. But we know that expectation of x of t is nothing but equal to the mean or the mean of the random process, or we also call it as an ensemble mean. So now we'll focus on E of x of t. So therefore E of x of t is equal to 1 by 2t minus t to integration between minus t to plus t. So we will substitute this E of x of t without angular bracket here, that is nothing but the mean of the random process or ensemble mean denoted by mu x. This is mu x is constant, so we take it outside, mu x by 2t integration between minus t to plus t dt. Integration of dt is nothing but t, the limits are minus t to plus t. So minus t in blue color lower limit and plus t in the upper limit here. So therefore mu x by 2t, then t minus of minus t will become equal to t plus t here. This is nothing but equal to mu x by 2t into 2t. So 2t will get cancelled out each other in numerator and denominator, and we are left with expectation of the average of, that is the x of t, is equal to mu x. So therefore ensemble mean is equal to that of the mean of the time average. So therefore for a ergodic process it is proved from the above, that is mathematical derivation, that mean of the time average is equal to the ensemble mean. In this case mean of the time average is left hand side denoted in red color, E of x of t, and mu x stands for the ensemble mean as we have discussed earlier. This is one sort of, that is observation or conclusion we come to the with respect to the ergodic random process, which is also a feature or the characteristic of any ergodic process. Second question, a numerical problem. We just approach this. For the random process, x of t is equal to a cos omega c t plus theta, where a and omega c are constants, but theta is called as a that is theta is a random process or a random variable, but it is called as a capital theta, is distributed uniformly between plus or minus pi. So from minus pi to plus pi, it is uniformly distributed. Show that this process is ergodic in nature, or it is an ergodic random process. So we have to prove that x of t is ergodic random process if we are having a and omega c are constants and theta is a random variable which is distributed uniformly between minus to plus pi. So this is the question at the hand here. The solution for this is the sample function, that is x of t, obtained from the random process x of t is equal to. So therefore the sample function is x of t in lowercase. It is obtained from random process capital X of t as follows. So therefore sample function is denoted by lowercase x of t and random process is denoted by capital X of t here. X of t is equal to a into cos omega ct plus theta as given here, and theta is some constant which is assuming a value within the range minus pi to plus pi. Now the autocorrelation function or ACF or averaging over time is written as below. So we know that autocorrelation function is nothing but that is product of x of t with x of time shifted version of itself, that is x of t plus tau. Then the averaging over time is indicated by the angular braces here which are placed on both the sides. So within the angular braces you find the ACF and average is applied over the ACF here. So this is nothing but equal to limit as t tends to infinity 1 by t integration from minus t by 2 to plus t by 2 x of t into x of t plus tau into dt. So therefore ACF is denoted here on the right hand side within the integral symbol here. So this is an integrand. This is equal to apply the limits t tends to infinity, then the equation is manipulated as follows. Limit t tends to infinity 1 by t between the limits minus t by 2 to plus t, and this is x of t. The definition of x of t as given in the problem here is a cos omega c t plus theta. So that is substituted here in the first quantum, right? This quantum a cos omega ct plus theta, this is the first term. Next one, instead of only t we are having t plus tau. In the above equation, wherever lowercase t is there, you apply the uppercase, that is the t plus tau here as in this particular case. So the equation is manipulated as second term as x of t plus tau is nothing but equal to a into cos omega c. So here t is there, instead of t you have to substitute t plus tau. So that is substituted here plus theta as it is and dt. So next we have to perform the integration of these things. A into a square cos omega ct plus theta first term, second term portion remaining which is in this that is term is cos omega ct plus omega c tau plus theta. Once you multiply omega c inside the parenthesis with every term here, this is the equation we get for the cosine term in dt. But we know that cos a into cos b is nothing but equal to 1 by 2 of cos a plus b plus cos a minus b, that is average of cos a plus b plus cos a minus b, that is divided by 2 here. So therefore using this trigonometric identity we substitute in the above integrand within the integration and the integrand respectively here. So this is equal to, again apply the limits as before, a square then 1 by 2 cos of 2 omega ct, right? So therefore we come to the conclusion that a is there, you are having omega ct plus omega ct is 2 omega ct plus omega c tau plus 2 theta plus cos omega c tau here. So therefore we go for applying this after doing the a plus b, that is addition and subtraction and all those things here for the entire equation. Finally we get this a square by 2 is taken outside, the limits of as t tends to infinity 1 by t integration between the limits cos 2 omega ct plus omega c tau plus 2 theta plus omega c tau. Now this is the quantum within the square bracket here. So this is nothing but equal to again a square, and take it outside. Within the square braces, the first term has cosine of 2 omega c is taken outside. See 2 omega c is there, and again omega c is there, and 2 theta is there, and then plus cos omega c tau is there. So therefore 2 omega c is taken, then t plus tau plus 2 theta plus cos omega c tau is there. So this is equal to 2 cos 2 omega c of t plus tau plus 2 theta into dt. So integration between these particular limits is separate cosine term we are going to perform on this. So first term integration plus second term again integration, but the limit is common for both these things inclusive of the a square by 2 term. Next we can focus on the first part of the integrand. So therefore this is integration, this particular portion first integrand in our equation is periodic in nature because t plus tau, whatever is happening within the t, the same thing is repeating after even after the t plus tau. That means it is periodic in nature. So the above equation is periodic function of t. Therefore, the first part of the integrand, this entire part will become equal to 0. Next, we are left with second part, that is cos omega c tau. Therefore, the second part of the integrand, that is integration minus t by 2 to plus t by 2 cos omega c tau dt is equal to take cos omega c tau outside because we are performing integration with respect to the dt. So we will be getting lowercase t here, cos omega c tau as before multiplied by, when you apply the integration with respect to dt, then t by 2 by minus t by 2. So plus t by 2 and minus t by 2 are the upper and lower limits respectively, and we have to substitute for lowercase t. Upon substitution, this equation is manipulated as cos omega c tau into t plus 2 by t by 2 plus t by 2. Addition we can perform and do all those things. 2t by 2 will cancel out each other and we are only capital T which is taken outside. So ultimately this second part of the integrand will become equal to t cos omega c tau. Therefore integration between minus t by 2 to plus t by 2 cos omega c tau dt is equal to t into cos omega c tau here. So this is one conclusion. Now we'll come to this average of the, that is autocorrelation function here. So therefore average autocorrelation function is denoted by, or ACF is denoted by x of t into x of t plus tau is equal to a square by 2 limit t tends to infinity 1 by t into t cos omega c tau. So here in this capital T in the numerator and denominator, we both cancel out each other and we are left with right hand side portion a square by 2 limit t tends to infinity, only cos of omega c tau is left out. So therefore average of the ACF autocorrelation functioning over the time is nothing but x of t into x of t plus tau, and averaging is equal to a square by 2 into cos omega c tau. So this is nothing but the right hand side portion as we have derived before. This can be denoted by a single mathematical notation, that is Rx into tau here. So this is autocorrelation function of random process x with the time difference equal to tau here. This is also denoted in the left hand side x of t original, x of t plus tau time shifted version. When you correlate, this is equal to Rx of tau. Now basically from the theory as well as the numerical problems and derivation, we can observe certain important things here. So main inferences are autocorrelation function or averaging over time is similar or same as the ensemble autocorrelation. So therefore averaging over time, if you find the ACF, even the ACF value of the ensemble also will be same numerically. Similarly, the mean and variance of the x of t which is taken over the time are same as the ensemble mean and variance. That is also proved from the above mathematical equations and numerical problems here. So satisfying both these characteristics, we come to the conclusion that given a random process x of t, any random process, in this case it is denoted by x of t, it is an ergodic random process upon satisfaction of the above two conditions. And this is it. Thank you.